Welcome to AI and Machine Learning Deep Dives. Today, we are going to embark on really an insightful journey, I think, to unpack one of the most powerful and versatile algorithms in the entire machine learning toolkit. I'm talking about random forests.
Ah, random forests.
You've probably heard the name. Maybe you've even, tinkered with them in your own projects. But our mission today is to truly demystify their inner workings. We want to understand not just what they are, but maybe more importantly, how they achieve their remarkable performance.
Exactly. Whether you're, a seasoned practitioner or maybe just starting your exploration into machine learning, we're aiming to go deep. We'll break down the foundational concepts, really explore their fascinating mechanics, talk about those critical hyperparameters that unlock their full potential.
Right, the tuning part.
Yeah, the tuning, and also highlight how you can navigate some common pitfalls to really master their use for, well, almost any data problem you might face. They're that versatile.
I'm really looking forward to this deep dive too. It's, for me, a perfect example of how seemingly simple building blocks, in this case, individual decision trees can come together.
Right.
They form something far greater, much more robust, and frankly, incredibly powerful.
Yeah, and we'll show you how a touch of carefully engineered randomness can actually lead to immense stability and predictive power. It's a
Yeah.
concept that maybe feels a bit counterintuitive at first glance, doesn't it? But it's just so incredibly effective in practice.
Okay, so let's start right at the very beginning. What exactly is a random forest, at its core? Let me try a simple analogy. Imagine you have an entire panel of expert decision makers, right?
Mhm.
Each with their own unique perspective, all weighing in on some complex problem simultaneously.
Mhm.
Now, instead of relying on the judgment of just one individual, no matter how skilled they are, you combine the insights, let's say, the collective wisdom of that entire group. And you arrive at a much more accurate, much more robust prediction. That fundamentally is what a random forest accomplishes in machine learning.
That's a great way to put it. It's what we call an ensemble learning method. Ensemble meaning group. It strategically combines the predictions from multiple individual decision trees. So you're truly leveraging that wisdom of the crowd principle, but applying it directly to your data.
Yeah, that wisdom of the crowd analogy is just so apt, I think. It perfectly captures the essence of how random forests operate. Like when you're tackling classification tasks, say, trying to predict whether a customer will churn or if an image contains, I don't know, a cat or a dog, the random forest arrives at its final decision through a majority vote.
Right. A democratic process,
Yeah,
basically.
exactly. So if you have, let's say, 100 individual trees in your forest, and maybe 70 of them predict customer churn, then the collective final prediction of the whole forest will be customer churn.
It smooths out the individual errors, the quirks of any single tree.
And it's just as effective for regression problems, too, where the goal is predicting a continuous numerical value.
Like house prices or temperature forecasts, things like that.
Right. In those scenarios, the random forest's output isn't a vote, but it's actually usually the simple average of the predictions generated by all the individual trees.
And that averaging effect is really a cornerstone of its power. It helps stabilize the predictions, makes them less sensitive to outliers, things like that.
It's quite remarkable how enduring this concept has proven to be, isn't it?
Yeah, it really is. The foundational idea, well, it was actually introduced by Tin Kam Ho way back in 1995. But then it was later significantly refined and really popularized by Leo Breiman and Adele Cutler. Breiman's work in particular was just so impactful that he even trademarked the term random forest.
Wow, I didn't know it was trademarked.
Yeah,
Yeah.
and it rapidly became a cornerstone algorithm in machine learning, pretty much because of its exceptional adaptability and really robust performance across just a vast array of problems.
And I think what's absolutely crucial for people to grasp here is that each individual tree within this, well, metaphorical forest,
Mhm.
it isn't trained on the entire data set, nor does it see all the same features every time it makes a decision.
Exactly. That deliberate choice to train on subsets of data and features is fundamentally key to its power. We'll definitely dig into why this randomness is such a strength.
Okay, but before we dive into the how of random forests, maybe we should first understand their most basic building block, the single decision tree.
Good idea. A single decision tree on its own is actually a pretty simple, quite intuitive model. It essentially forms a set of rules, you can think of it like a flow chart, to categorize data or make predictions.
Right, like a series of yes-no questions.
Kind of. Imagine it splitting your observations based on various attributes or features, always aiming to create groups or nodes that are as pure as possible. Pure meaning, ideally, all the samples in that group belong to the same class or have very similar values if it's regression. And you want these groups to be as distinct from each other as possible.
So for example, in maybe a medical context, a decision tree might start by splitting patients based on age. Like if age is less than 60, go down this branch. If age is 60 or more, go down that branch.
Right.
Then maybe it splits further based on, say, cholesterol levels or blood pressure within each of those age groups.
That's exactly it. And these trees are remarkably flexible in how they actually make those splits. They don't just guess. They pretty exhaustively evaluate every possible cut point for a given feature to find what they consider the best split at that particular node.
And best usually means reducing impurity the most, right? Using measures like Giugini impurity or entropy.
Precisely. Giugini impurity and entropy are basically ways to quantify the mixed-upness or disorder of a node. The algorithm consistently seeks the split that results in the largest decrease in this impurity. It wants cleaner, more homogeneous groups of data after the split. And this recursive splitting, it just keeps going until the nodes are perfectly pure, meaning, all samples in that node belong to the same category, or maybe until no further significant improvement can be made in terms of impurity reduction, or perhaps until some other stopping criterion is met, like a maximum depth.
Right, okay. So the result is this potentially very deep, very detailed set of rules.
It can be, yeah. Highly granular.
Now, despite how intuitive and flexible they sound, single decision trees come with some pretty significant drawbacks. And this is exactly where the genius of the random forest really shines, I think.
Absolutely. The biggest issue, the one everyone talks about, is their tendency to overfit the training data.
Especially when they're allowed to grow very deep without any constraints.
Right. And what does overfitting mean, practically? It means the tree learns too much about the specific, maybe even unique characteristics, and crucially, the noise present in your training data.
So it's like memorizing the answers.
Essentially, yeah, it effectively memorizes the training examples rather than truly understanding the underlying patterns. And this makes them brittle, unreliable when they face new, unseen data. They struggle to generalize.
Like you said, it's like preparing for a test by just memorizing the answers to specific practice questions instead of actually understanding the core concepts. You might ace the exact questions you practiced, but you'll likely struggle with any new variations or slightly different problems.
Couldn't have said it better. And if we connect this to the bigger picture, a single decision tree might be locally optimal, meaning, yeah, it finds the best possible split at each individual node based on the data it sees at that point. But that doesn't mean it's globally optimal for the entire data set or the underlying problem.
And they're super sensitive too, right?
Extremely sensitive. Even minor changes in the training set, like adding or removing a few data points, can lead to a completely different tree structure. This results in what we call high variance in their predictions. One dataset might give you one tree, a slightly different dataset gives you a wildly different tree.
Which makes a standalone decision tree far less reliable for making robust predictions on new data. And that's the problem we really need to solve.
Exactly.
Okay, so that raises the critical question. How do we effectively address these fundamental issues, this overfitting, this instability that plagues single decision trees?
Well, the elegant solution, the random forest solution, lies in introducing carefully controlled randomness and, crucially, combining many, many trees together.
All right, the ensemble idea again.
Yep. The random forest builds on a powerful technique known as bootstrap aggregating. You often hear it just called bagging.
Bagging, okay.
This is where a significant part of the magic truly begins. Instead of training each individual tree on the exact same entire dataset, we create multiple distinct datasets. And we do this by randomly sampling from the original dataset with replacement.
Okay, with replacement, let's unpack that. That means when you're creating a new dataset for one tree, you pull samples from the original data, but after you pull one, you put it back in.
Exactly. So a single data point from your original dataset could actually be selected multiple times for a particular tree's training set.
While other data points might not be selected at all for that specific tree.
Precisely. And what's really fascinating and incredibly useful is that this process typically leaves about, on average, 1/3 of the original data points out of any given bootstrap sample.
Ah, the famous out-of-bag samples.
The very same, out-of-bag or OOB samples. And they become incredibly useful later on for getting an unbiased evaluation of our model's performance, as we'll see.
So this whole process of creating these slightly different data sets for each tree, this bagging, it introduces a fundamental level of diversity among them, right?
That's the key. It ensures they don't all learn the exact same patterns or make identical errors. It forces each tree to see the data from a slightly different perspective, leading to, well, distinct viewpoints in the final ensemble.
Okay, so that's one source of randomness, sampling the data differently for each tree using bagging. But random forests take it a step further, don't they?
They do. Beyond just sampling the data, the random forest algorithm employs what we call random feature selection. Sometimes you might hear it called feature bagging, or maybe the random subspace method.
Okay, random features too. How does that work?
It's another brilliant layer of decorrelation, really. At each and every split point within an individual decision tree, when the tree is deciding which feature to split on. Instead of considering all possible features to find the absolute best split, the algorithm only considers a random subset of those features.
Okay. So if I have, say, 100 features in my data set.
Then for any given split, a tree might only be allowed to look at, say, 10 of them, or maybe 20. It depends on the setting, but it's only a subset.
And why is that helpful? Doesn't that limit the tree?
It does limit the tree at that specific split, but it makes the forest stronger. This strategy makes each tree not just diverse in terms of the data it sees, thanks to bagging, but also in the features it prioritizes for splitting. It prevents a situation where one single, very strong predictive feature completely dominates the decision-making process in all the trees.
Right, because if every tree just picked that same super strong feature first, they'd all end up looking very similar.
Exactly, and that would undermine the whole point of the ensemble, the diversity. This random feature selection forces the trees to explore alternative features, maybe weaker ones individually, but potentially useful in combination. It encourages them to develop different internal logic paths.
Are there standard rules for how many features to pick randomly?
There are common heuristics, yeah, rules of thumb. For classification problems, a very common starting point for the size of this random subset is the square root of the total number of features.
So if you have 100 features, square root is 10. You'd consider 10 random features at each split.
Typically, yes. And for regression problems, a more common heuristic is to use about 1/3 of the total features.
But these are just starting points, right? You might need to tune this.
Absolutely. They're good starting points,
Yeah.
but the optimal number can definitely vary depending on the data set. It's another hyperparameter you can tune. If you use too many features, the trees might become too correlated again. If you use too few, the individual trees might become too weak to learn effectively.
So it's this beautiful combination, the synergy of these two random processes
Bootstrap sampling of the data.
and random feature selection at each split.
Yep. That's what creates a model that is significantly more robust to noise, far less likely to overfit, and often remarkably more accurate than any single decision tree could ever hope to be on its own.
It really is like an embodiment of collective intelligence, isn't it?
It is. Think of it like having a large group of doctors examine a patient. Each doctor gets slightly different subsets of the patient's records and maybe focuses on different sets of symptoms or tests.
Okay.
When you combine their diverse, independent diagnoses, the overall conclusion is far more reliable and robust than relying on just one single doctor's opinion. It smooths over individual biases or missed details.
That makes sense. It averages out the errors and focuses on the consensus.
Precisely. It yields a stable, highly accurate result.
Okay, that brings us to takeaway number 1. Random forests are powerful ensemble models that combine many decision trees. Using bootstrap sampling and random feature selection to introduce diversity, reduce overfitting, and provide more robust and accurate predictions than any single tree.
Well summarized.
Now that we've got the mechanics down, let's really explore why random forests are so highly valued across the whole machine learning landscape. What makes them stand out from the crowd?
Well, their greatest strength, I think, without much debate, is their ability to significantly improve prediction accuracy. That's usually why people turn to them first. By averaging the results from that diverse set of trees we talked about, they effectively mitigate that critical risk of overfitting that so often plagues individual decision trees.
So better accuracy and less overfitting. That's a powerful combo already.
It is, and related to that is their robustness. What's truly fascinating is how individual errors from just one tree, maybe a tree that got a weird sample of data, just get averaged out by the collective predictions of the entire forest.
So they're less sensitive to weird data points.
Much less sensitive. It makes the overall model far less sensitive to noisy data or outliers, which, let's be honest, are incredibly common challenges in almost any real-world data set you'll encounter.
Yeah, data is rarely perfectly clean.
Never. Imagine you have a few corrupted data points. One tree might make a really poor prediction because of them. But when that prediction is averaged with hundreds of others that weren't unduly influenced by those specific noisy points, the overall impact is just minimized. That inherent resilience is a huge practical advantage.
And they're versatile too, right? I hear they handle complex data well.
Extremely versatile. They work exceptionally well, even when you have more features than observations, what we call high-dimensional data or fat data.
Right, like in genomics or some text analysis problems.
Exactly. This is absolutely critical in today's complex data sets, where more traditional statistical methods might really struggle or even completely fail due to the infamous curse of dimensionality.
And they handle different types of variables easily.
Yeah, that's another big plus. They can seamlessly manage both categorical variables like country or product type and continuous variables like age or price within the same model, and often without requiring extensive complex pre-processing just to make them compatible.
That saves a lot of headaches and data prep.
It really does. You don't have to spend hours trying to figure out how to convert everything to one single numerical type, which can sometimes lose information anyway.
Okay, so they're accurate, robust, handle complex data. What else? You mentioned insights earlier.
Right. There's more to it than just raw predictive power. Random forests provide really valuable insights, which is a massive bonus for practitioners who want to understand their data better, not just get a prediction. They give you what we call feature importance scores.
Yes. Feature importance. How does that work?
Basically, these scores quantify how much each variable, each feature contributed to the model's performance, usually measured by how much it helped reduce impurity across all the splits and all the trees where that feature was considered.
So it tells you which variables were most influential in making the predictions.
Exactly. This helps you understand your data better, gives you critical clues for further analysis, or helps you refine your model by focusing on the most impactful features. This level of interpretability, even though the overall forest is technically a complex black box of many trees, is incredibly valuable for making real-world decisions based on the model.
And I've heard they're relatively easy to use, especially for beginners.
That's another great point. From a practical standpoint, for people just diving into machine learning, random forests are often an excellent starting point. Why? Because they frequently provide strong baseline performance right out of the box, even with just the default settings in most libraries.
So less fiddling required initially compared to some other algorithms.
Often, yes. They typically require less intensive hyperparameter tuning compared to algorithms like, say, support vector machines or gradient boosting machines, just to get a decent result. This accessibility, coupled with their power, is a pretty rare and attractive combination.
Plus, I think you mentioned they handle missing values okay.
They do, often quite effectively. They have built-in ways to handle missing values during training and prediction, often without requiring you to perform complex imputation steps beforehand. You don't necessarily have to fill in all the gaps perfectly before feeding the data in.
That definitely lowers the barrier to entry.
It does. It makes your whole data preparation process significantly less of a headache.
And connecting this back to the bigger picture, their versatility, you said, extends even beyond standard prediction tasks.
Yeah, they can be adapted for unsupervised learning tasks too, like clustering. You can use the proximity measures derived from how often pairs of samples end up in the same leaf node across the forest to understand data structure.
Interesting.
But circling back to supervised learning, what's truly fascinating and maybe underappreciated is how well they excel at handling nonlinear relationships between variables.
Ah, right. When the connection isn't just a straight line.
Exactly. This is a super common, often difficult challenge in real-world data where simple linear models just won't cut it. Random forests, because they're built from decision trees which naturally partition the feature space, are inherently good at capturing these complex, nonlinear interactions between features without you having to explicitly define them. That's a major reason for their widespread adoption and continued relevance.
Okay, so this sounds amazing in theory, but what does all this mean for practical, real-world applications? Where are random forests actually making a difference?
Oh, they're far from just theoretical constructs. They are genuine game changers, actively deployed across a huge array of sectors. Take healthcare, for instance. They're widely used for predicting patient outcomes, diagnosing diseases based on complex clinical data, think medical images, lab results, patient history.
So helping doctors make better diagnoses.
Exactly. Aiding in earlier and more accurate diagnoses. They're used for identifying high-risk patients who might need intervention sooner. Imagine the impact of studies showing their effectiveness in predicting things like heart disease or diabetes risk. That's potentially life-saving technology right there.
Wow. And finance. I imagine they're big there too.
Absolutely massive in finance. Random forests are heavily relied upon for critical tasks like fraud detection, spotting those subtle, unusual patterns in transactions that might indicate fraud.
Stuff that humans might miss easily.
Precisely. They're also core components in credit scoring models, helping banks assess the risk of borrowers defaulting and in more comprehensive financial risk assessment frameworks.
Could you give some concrete examples?
Sure. Think about the potential tangible benefits. Maybe Bank B increases its fraud detection accuracy by, say, 50% by leveraging random forests to spot those unusual transaction patterns that might evade simpler rule-based systems.
That's huge for a bank.
Or maybe financial institution A significantly reduces its loan default rates by 30% because their random forest-based credit scoring model is just better at identifying risky applicants. That leads to more responsible lending and healthier financial portfolios overall.
And it's not just about risk, is it? What about market prediction?
Right. Beyond risk, they're also crucial for forecasting market trends, enhancing sophisticated investment strategies, and optimizing portfolios. They can provide deep insights into potential market shifts. You could imagine a firm, say Hedge Fund F, improving their market forecasting accuracy by maybe 40%, directly impacting their trading strategies and ultimately their bottom line.
Okay, healthcare, finance.
What?
What else?
Well, in marketing, they assist with nuanced customer segmentation, finding distinct groups of customers based on their behavior or demographics. And also with highly accurate preference prediction, helping companies target their advertising much more precisely and personalize customer experiences effectively.
Makes sense. Knowing what customers want.
And even in fields like ecology, they're used. They can predict species distribution based on environmental factors or help assess environmental stability, aiding vital conservation efforts and climate modeling.
That's quite a range.
It is. And I think the balance they strike between achieving high performance and also providing those valuable feature importance insights makes them incredibly attractive. They work well for both initial exploratory studies, where you're just trying to understand the data, and for building robust production-level models that need to be reliable day in, day out across all these diverse fields.
Okay, that's really compelling. That brings us to takeaway number 2. Random forests offer unparalleled accuracy and robustness, can handle complex, high-dimensional data with various types of features, and provide valuable insights into feature importance, making them indispensable across healthcare, finance, and many other real-world applications.
Couldn't agree more.
All right, here's where it gets really interesting, I think, and where you, as a practitioner listening in, can significantly elevate your random forest models from just good to great. While random forests are certainly powerful, even with default settings, as you said, their performance can often be dramatically optimized by carefully tuning their hyperparameters.
Ah, the tuning knobs.
Yes, exactly. These aren't values that the model learns directly from the data during the training process itself. Instead, they are settings you define before you start training.
And they directly influence how the model performs, right? They control its complexity.
Its complexity, ultimately its accuracy, and critically, its ability to generalize effectively to new unseen data. That generalization part is key.
And ignoring hyperparameter tuning, that's a really common pitfall, isn't it? People often just take the defaults.
It really is. You can leave a substantial amount of performance just sitting on the table if you don't tune.
Yeah, think of it like fine-tuning a high-performance engine in a race car. You want to get the absolute best mileage and speed out of it.
Right. You wouldn't just expect that race car to perform optimally with its factory default settings, would you?
Probably not. The same principle applies here. A well-tuned random forest can mean the difference between just okay performance and truly exceptional production-ready results that you can rely on.
Okay, so let's talk specifics. We can control the growth and complexity of each individual tree, and by extension, the behavior of the entire forest, using a handful of these key hyperparameters. Where should we start? Maybe max depth.
Yeah, max depth is a classic one. This parameter, quite simply, sets the maximum depth that each individual tree in the random forest is allowed to grow. It basically dictates the longest possible path from the very first decision point, the root node, down to a final prediction, a leaf node.
And if you don't limit it, if you just let the trees grow as deep as they want.
Well, if you leave max depth unconstrained, those individual trees can become extremely deep. They get overly specific, and they start, as we discussed, essentially memorizing the training data, including all its noise and quirks. That's overfitting.
So limiting max depth helps prevent that overfitting.
Exactly. It's a direct way to control complexity. But there's a flip side. If you set max depth too small, too shallow, then the model might be too simple. Underfitting.
Precisely. It might lead to underfitting, where the model is just too simplistic, too constrained to capture the complex underlying patterns in your data.
So we're always looking for that sweet spot, that Goldilocks zone.
Always. We're aiming for that point where the performance on your training data and the performance on your unseen test or validation data are reasonably close and both are good. That suggests your model is generalizing well.
Okay, max depth. What's next? Maybe min sample split.
Good one. Min sample split. This hyperparameter tells a decision tree the minimum number of data samples or observations a node must contain before it can even be considered for splitting further.
Ah, okay. So if a node only has a few samples, it stops splitting.
Potentially, yes. The default value in many libraries is often just 2, which means a node can be split as long as it has at least 2 samples, which allows trees to split until nodes are incredibly pure, right? Potentially leading to overfitting again.
Exactly. It allows very fine-grained splits, often resulting in very deep trees and that overfitting risk. So increasing the value of min-sample split acts as a constraint. It reduces the number of possible splits overall, preventing the tree from growing excessively large and capturing noise.
But again, if you set it too high.
Right. If you set this value too high, the tree might become overly cautious. It might fail to make significant informative splits, even when they would be beneficial, leading to underfitting because it's just too constrained to learn the meaningful patterns.
Makes sense. And closely related is min-sample sleeve, right? How's that different?
It's similar in spirit, but subtly different. Min-sample sleeve specifies the minimum number of samples that must be present in a leaf node that's a final terminal node after a potential split has occurred.
Okay, so min-sample split is about the parent node before the split, and min-sample sleeve is about the child nodes after the split.
You got it. Setting a higher value for min-sample sleeve is another very effective way to prevent overfitting. It ensures that your final decision points, the leaves of each tree, aren't based on some arbitrary, tiny handful of samples, which could easily just be noise or outliers.
So if a potential split would result in one of the new leaves having fewer samples than min-sample sleeve,
then that split is simply not made. The algorithm rejects it, and the parent node becomes the final leaf instead.
and again, the danger of setting it too high is underfitting.
Same trade-off. Just like min-sample split, setting min-sample sleeve too high can cause the model to underfit. It might become too generalized, too smooth, unable to pick up on important, finer-grained nuances in your data.
Okay, so we have max depth, min-sample split, min-sample sleeve. What about max leaf nodes?
Right, max leaf nodes. This one directly restricts the total number of terminal nodes or leaves that any single tree in the forest is allowed to have.
So instead of limiting depth, you're limiting the total number of endpoints.
Exactly. If, after considering a split, the total number of terminal nodes in the tree would exceed this specified limit, the splitting process just stops for that tree.
So it's yet another way to control the overall complexity and size of the individual trees.
Yep, another effective method to control tree growth and prevent overfitting by simply capping the tree's ability to create too many specific, potentially memorized rules or regions.
And presumably setting this too low leads to underfitting.
Same story. A very small value here can definitely lead to underfitting, making the individual trees too simple to learn effectively. Finding the right balance among all these parameters, max depth, min-sample split, min-sample sleeve, max leaf nodes, is really crucial for getting optimal performance. They often interact with each other.
Okay, those control the individual trees. Now let's shift focus to the parameters that specifically govern the ensemble nature of random forests, the ones that define the forest itself. First up, probably the most obvious one, nestimators.
Ah, yes, nestimators. This one's pretty straightforward. It's simply the number of individual decision trees that will be built and then combined within your forest.
And the intuition might be, well, more trees are always better, right?
That's a common thought, and initially it's generally true. As you increase the number of trees, you typically see a sharp increase in the model's performance and stability.
Why is that?
Because you're averaging more predictions, more diverse opinions, if you like. This effectively reduces the variance of the overall model. The more trees you average, the smoother and more reliable the collective decision becomes.
But does it keep getting better indefinitely?
No, there's usually a point of diminishing returns. Performance tends to plateau or stagnate after a certain number of trees. Now, the good news is, adding more trees beyond this plateau point generally won't degrade the model's accuracy. It doesn't usually start overfitting just because you add more trees, unlike some other algorithms.
Okay, that's good to know. But what's the downside then?
The downside is purely computational. Adding more trees, especially beyond the point where performance plateaus, will significantly increase the time it takes to train the model and also the time it takes to make predictions. Plus, it increases the memory consumption, which could become an issue with really large forests or limited hardware resources.
So what's a typical number? What do people usually use?
Well, in popular libraries like scikit-learn, the default for newer versions is often set to 100 trees. And that frequently strikes a pretty practical balance between getting most of the performance gain and keeping the computational cost reasonable.
But is 100 always enough?
Not necessarily. For many applications, a good sweet spot typically ranges anywhere between, say, 100 and maybe 500 trees. But it's always worth testing this for your specific data set. Sometimes you might need more, sometimes 100 is perfectly fine.
Okay, nestimators. What about max samples? You mentioned that earlier with bagging.
Right, max samples. This hyperparameter lets you control the fraction, or sometimes the absolute number, of observations from the original dataset that is given to any individual tree when creating its bootstrap sample.
So instead of always giving each tree a sample the same size as the original data set, but sampled with replacement, you can give it a smaller sample.
Exactly. It's not always necessary or even beneficial to give each tree access to the full data via the standard bootstrap. In many cases, especially with large data sets, the model performance can actually reach its maximum when a fraction less than the full data set is used for each tree's sample.
And the benefit there is speed.
Primarily speed, yes. Using smaller samples can drastically reduce training time without sacrificing accuracy, sometimes even improving it slightly due to increased diversity. This can be particularly useful for very large data sets where training on the full data for every single tree would just be computationally prohibitive.
But the best fraction depends on the data.
Absolutely. The optimal fraction, whether it's 0.7, 0.8, or something else, will vary by dataset. It's another parameter that might require some experimentation or tuning.
Okay, and then there's max features, which we also touched on, the random feature selection part.
Yes, max features. This one controls how many features the model considers when it's searching for the best split at each node of an individual tree. Remember, the random forest deliberately chooses only a random subset of features at each split to find the best one among that subset.
Right, to promote diversity and stop strong features from dominating.
Exactly. Now, increasing max features initially tends to improve performance because it gives the trees more potentially good options for finding strong splits.
But if you set it too high, if you let it consider almost all features,
Well, if you set max features too high, maybe close to the total number of features, then the individual trees within your forest can start to become more correlated with each other again. They're all looking at mostly the same features, so they start making similar decisions.
and that undermines the ensemble effect.
It does. The diversity decreases and the benefit of averaging diminishes. In extreme cases, if max features is set to the total number of features, you lose that feature randomness component entirely, and the model might start to overfit more easily, behaving more like just standard bagging without the random subspace method.
So it's a real balancing act again. We need enough features to find good splits, but not so many that the trees become clones.
Precisely. And those conventions we mentioned earlier are good starting points. For classification, try squart number features. For regression, maybe number of features 3. This carefully controlled randomization at the feature level is absolutely key to creating the necessary diversity among trees that makes random forests so powerful and robust. It's a strategic limitation that actually yields a stronger overall model.
Okay, those seem like the main ones. Are there any other important parameters worth mentioning quickly?
Yeah, a few others come up often. Criterion is one. This defines the actual mathematical measure used for judging the quality of a split. Common options are Gini for Gini impurity or entropy for information gain.
Does the choice matter much?
Often the practical results are quite similar, though sometimes one might perform slightly better on a specific dataset. Gini is often the default and slightly faster computationally. Then there's njobs. This is a very practical parameter for speeding things up. It allows you to use multiple CPU cores on your computer to train the trees in parallel.
Ah, Because the trees are independent, you can build them at the same time.
Exactly. Setting jobs to Manish 1 typically tells the library to use all available CPU cores, and this can dramatically speed up the training time, especially if you have a large number of trees, nestimators, and a multi-core processor.
That's very useful.
And finally, OOB score. This is usually a Boolean flag. True-false. If you set it to true, the model will automatically use those out-of-bag samples, the data points not seen by each particular tree during its training, to calculate an internal, unbiased estimate of the model's performance.
So it gives you a validation score without needing a separate validation set.
Correct. It saves you the effort of splitting your data manually for simple validation, and it's a very powerful feature unique to ensemble methods like random forests that use bagging. Very handy for quick performance checks.
Okay, wow. That's quite a few knobs to potentially turn. So with all these parameters, how do we systematically find the optimal combinations for our specific data set? We can't just guess, right?
Definitely not just guess. That would take forever and likely miss the best setup. We use various systematic tuning techniques. Grid search is probably the most well-known method.
How does grid search work?
It's pretty exhaustive. You define a grid of specific hyperparameter values you want to test, like maybe try a nestimator is equals 100, 200, 300, max depth equal 5, 10, 15, and max features, score log 2. Grid search will then train and evaluate a model for every single possible combination of these values.
Every single one. That sounds thorough.
It is very thorough. It guarantees you'll find the best combination within the grid you specified. But the downside is it can be computationally very expensive, especially if you have many hyperparameters or large ranges of values to explore. The number of combinations explodes quickly.
Right. Imagine trying every key on a massive keyring to find the right one.
Exactly. So a more efficient and often equally effective alternative is random search.
Random search, how's that different?
Instead of trying every single combination in a predefined grid, random search randomly samples a fixed number of hyperparameter combinations from specified distributions or ranges.
So it just picks, say, 50 random combinations and tries those.
Pretty much, yeah. You tell it how many combinations to try. It might sound less systematic, maybe even a bit haphazard, but in high-dimensional parameter spaces where you have many hyperparameters, and maybe only a few of them have a truly significant impact on performance, random search can often find very good, sometimes even optimal combinations significantly faster than grid search.
Because it's not wasting time on exploring systematically bad regions of the parameter space.
Exactly. It's like, throwing darts at a dartboard. You might hit the bullseye, or at least a really good spot near it, just by chance much quicker than meticulously trying every single tiny square on the board. It's often much more efficient for the same computational budget.
Okay, grid search, random search. Is there anything more advanced?
There is. For those really pushing the boundaries or seeking maximum efficiency, there's Bayesian optimization.
Bayesian optimization sounds sophisticated.
It is a bit more complex, but very powerful. Unlike grid search or random search, which are kind of blind searches, Bayesian optimization actually learns from past evaluations. It uses the results of the previous hyperparameter combinations. It has tried to build a probabilistic model, often using Gaussian processes, of how the performance metric, like accuracy or error, behaves across the hyperparameter space.
So it uses that model to decide where to search next.
Precisely. It intelligently directs the search towards regions of the hyperparameter space that the model predicts are most likely to contain the optimal values, while also exploring areas with high uncertainty. It aims to find the optimum more efficiently by focusing its efforts.
And does it work better?
Studies often show that Bayesian optimization can provide slightly higher accuracy or find optimal parameters significantly faster in terms of the number of evaluations needed compared to simpler methods like grid or random search, especially for complex problems or expensive to evaluate models. It's generally considered a smarter, more sample-efficient way to search.
Fascinating. Okay, lots of options for tuning there.
That brings us to takeaway number 3. Hyperparameters like max depth, min sample sleeve, nestimators, and max features are crucial for optimizing random forest models, controlling their complexity and preventing both overfitting and underfitting. Their optimal values are found through systematic tuning techniques such as grid search, random search, or Bayesian optimization.
All right, so we've covered the power of random forests and the importance of fine-tuning them. Now let's pivot slightly and talk about avoiding some common missteps or pitfalls when working with them. One area where I think practitioners, especially newer ones, often make mistakes is in interpreting those feature importance scores we mentioned earlier.
Yes.
A very common issue. These scores, which tell you roughly how much each feature contributed to reducing impurity across all the trees. They're incredibly valuable tools for understanding your data, no doubt. But the common mistake is treating them as some kind of absolute definitive ranking of a feature's real-world relevance, or, even worse, jumping to conclusions about direct causality. They provide insights, absolutely, but they aren't the whole story, are they?
Not at all. That's a crucial point. These standard impurity-based importance scores can be influenced by several factors that might lead to misinterpretation if you're not careful. For example, when you have multiple features that are highly correlated with each other, meaning they basically provide very similar information, their importance might get diluted or distributed somewhat arbitrarily among them by the model.
So a truly important underlying factor might appear less important because its effect is split across several correlated features.
Exactly. It can potentially underestimate the true collective impact of that underlying concept because the credit for its predictive power gets split.
What else can skew them?
Well, features with larger numerical scales, or those with more potential split points, like continuous variables compared to binary ones, might inadvertently appear more important simply due to how the impurity calculation works, not necessarily because they have more inherent predictive power.
Okay, so scale matters.
And here's another subtle one. Categorical variables that have a very large number of unique levels, what we often call high cardinality features, can sometimes be artificially favored by these impurity-based importance measures. It's a known bias. This can skew the scores and give you a false sense of their individual importance compared to features with fewer levels.
Wow, okay. So how do we mitigate these issues? How do we get a more reliable picture of feature importance?
Good question. We recommend a multifaceted approach. First, don't just rely solely on the random forest's default built-in feature importance scores. Consider using multiple feature selection or importance techniques to cross-validate your findings. Maybe look at permutation importance, which is often considered more robust, especially regarding correlated features, or even more advanced methods like SHAP values.
So get a second opinion, basically.
Essentially, yes. It's also absolutely crucial to understand and analyze the correlation between your features before drawing firm conclusions from importance scores. If two features are highly correlated, their individual scores might be misleading.
Should we normalize features first?
Normalizing or standardizing your numerical features can help prevent scale bias from influencing the importance scores, so that's often a good practice. And perhaps most importantly, always try to validate your importance findings through robust domain expertise. Your understanding of the real-world problem, the context of the data, should always inform and temper your interpretation of these purely statistical scores. They're clues, not commandments.
That makes sense. Use them as a guide, but verify with other methods and domain knowledge.
Yeah.
Okay, that's feature importance. What about overfitting? This raises an important question I hear debated quite a bit. We frequently hear claims, sometimes quite strong ones, that random forests are inherently resistant to overfitting. Some people even go so far as to claim it's mathematically impossible for them to overfit. Is this actually true?
The random forests can't overfit myth.
Yeah.
It's a persistent misconception, and the reality is, well, more nuanced than that.
So they can overfit.
Yes, they absolutely can. Let's be clear. While the ensemble nature, the bootstrap sampling, bagging, and the random feature selection do significantly reduce their tendency to overfit compared to single, unconstrained decision trees, they are definitely not immune.
Okay, so why the misconception then?
I think it comes from the fact that adding more trees, nestimators, generally doesn't cause overfitting in the same way it might in, say, boosting algorithms. But that doesn't mean the model as a whole can't overfit the data for other reasons. Practical experience across countless data sets clearly shows that random forests can and do overfit. This is especially true when you're dealing with very small data sets or data sets that are highly homogeneous, where the patterns are maybe too easy to memorize, or, critically, if their hyperparameters are not tuned correctly.
And what are the signs? How would you know if your random forest is overfitting?
The classic sign is seeing exceptionally high accuracy or low error on the data you use for training, but then a noticeable, often quite dramatic, drop in performance when you evaluate the model on new, unseen validation or test data.
That gap between training performance and test performance is the red flag.
Exactly. It indicates the model has started to learn the specific noise and idiosyncrasies in your training set rather than capturing the genuine, generalizable underlying patterns. It's memorizing and not learning.
Okay. And conversely, underfitting is still possible too, right? If the model's too simple.
Absolutely. On the other end of the spectrum, underfitting occurs when your model is just too simplistic, too constrained to capture the complex patterns within your data adequately. This often happens, as we discussed, due to overly restrictive hyperparameter settings like max depth being too small or min sample sleeve being too large. It hobbles the model's ability to learn.
So how do we actively prevent overfitting in practice with random forests?
Well, you use those hyperparameters we talked about. You can strategically limit the maximum tree depth using max depth. You can increase the minimum samples required per leaf node with min sample sleeve, forcing the leaves to be based on more robust evidence. You also need to carefully control the number of trees. Nestimators, typically aiming for that sweet spot, maybe 100 to 500 trees, often provides a good balance without unnecessarily overcomplicating the model or computation time.
And validation is key here.
Crucial. Using rigorous cross-validation techniques is absolutely essential. It helps you get a reliable estimate of generalization performance and detect overfitting early by seeing how performance varies across different subsets of your data. And remember, the inherent mechanisms of random forests, the bootstrap sampling, and the random feature selection, they themselves act as built-in regularization techniques. They introduce just enough controlled variance and prevent individual trees from becoming too specialized, naturally reducing the overall risk of overfitting compared to simpler models.
Okay, so be aware of overfitting, tune parameters, use cross-validation. Got it. What about data preprocessing? Is that still important for random forests?
Oh, absolutely. Data preprocessing is the fundamental bedrock for any successful machine learning model, random forests included. Now, it's true that random forests are generally more robust to imperfect data than some other algorithms. They can handle a bit of messiness. Outliers might have less impact due to averaging. They don't strictly require feature scaling.
But they're not magic.
Exactly.
Yeah.
They are definitely not immune to issues arising from poor data cleaning or preparation. You must handle missing values appropriately. Even if RF has ways to deal with them, explicit imputation might be better. You need to identify and potentially address significant outliers that could still skew results, and just ensure overall data consistency and quality.
The old adage still holds, garbage in, garbage out.
It absolutely does. The best, most sophisticated algorithm in the world can't make sense of fundamentally flawed or nonsensical input data.
And what about categorical variables? Are there specific pre-processing pitfalls there?
Yeah, that's a common stumbling block, especially with random forests. While they can handle categorical features intrinsically in some implementations, careful preparation is often still needed or beneficial. For instance, just blindly applying one-hot encoding where each category becomes a new binary one feature can be problematic if you have high cardinality features.
Features with lots and lots of unique categories, like maybe zip codes or user IDs.
Exactly. One-hot encoding these can create a huge number of new, very sparse columns. This can blow up your feature space dimensionality, slow down training, and sometimes even degrade performance because the splits become less informative.
So what are the alternatives to one-hot encoding for those high cardinality features?
You need to consider other encoding strategies. Maybe ordinal encoding, if there's a natural order to the categories. Or more advanced methods like target encoding, using the target variable to encode categories but carefully to avoid leakage. Or count encoding, or even embedding techniques borrowed from deep learning. Sometimes you might also need to manage high cardinality features by grouping less frequent categories together into another category, or by applying some clever feature engineering based on domain knowledge.
And what about interactions between categories?
Good point. Always explore potential interactions between categorical features and between categorical and numerical features. These interactions can often hold significant predictive power that might be missed if you just treat each feature in isolation. Random forests are good at finding interactions, but good preprocessing can sometimes help surface them more easily.
Okay, so preprocessing still matters a lot. Final area pitfalls. Performance evaluation. What are common mistakes here?
A huge one is choosing the wrong metrics, or relying on just a single metric, especially accuracy. Blindly applying just one number can lead to incredibly misleading conclusions about your model's true effectiveness in the real world.
Particularly with classification, right? You mentioned accuracy being misleading for imbalanced data sets.
Exactly. For classification, while overall accuracy, the percentage of correct predictions, is the most common metric, it can be terribly misleading when you're dealing with imbalanced data sets where one class is much, much rarer than the others.
like fraud detection or rare disease diagnosis.
Perfect examples. Imagine detecting a rare disease that only affects 1% of the population. A model that simply predicts no disease for everyone would achieve 99% accuracy, but it's completely useless clinically because it never identifies the actual cases.
So accuracy isn't enough. What should we use instead for classification?
This is where metrics like precision, recall, and the F1 score become absolutely indispensable. Precision tells you, out of all the instances your model predicted as positive, for G predicted disease, how many were actually positive? It measures the accuracy of positive predictions. Recall, also called sensitivity or true positive rate, tells you, out of all the actual positive instances that exist in the data, how many did your model correctly identify? It measures how well the model finds the positive cases.
And F1 score.
The F1 score is the harmonic mean of precision and recall. It provides a single balanced measure that's particularly useful when you care about both minimizing false positives, good precision, and minimizing false negatives, good recall, especially with imbalanced data sets.
What about AUC-ROC?
The AUC-ROC area under the receiver operating characteristic curve is another powerful metric. It helps you understand the model's ability to discriminate between the positive and negative classes across all possible classification thresholds. It gives a more comprehensive view of the model's overall diagnostic or ranking ability.
Okay, that's for classification. What about regression, where we predict numbers?
For regression problems, we look at different metrics. Common ones include mean squared error, MSE, or root mean squared error, RMSE, which quantify the average magnitude of the errors, the difference between predicted and actual values. Lower is better. And R squared, coefficient of determination, which tells you the proportion of the variance in the dependent variable that is predictable from the independent variables. It indicates how well your model's predictions fit the actual values, with one being a perfect fit.
So choose the right metrics for the task. And how do we ensure the evaluation itself is robust?
The gold standard for robust model evaluation, as we've touched upon, is absolutely cross-validation. Don't just do a single train test split, because a single split might just be lucky or unlucky. Your test set might happen to be particularly easy or particularly hard. Cross-validation overcomes this. Techniques like k-fold cross-validation, where you divide your data into k-folds, say 5 or 10, and then iteratively train the model on k1 folds and test on the remaining fold, repeating this array times, this ensures your performance estimate is averaged across different data subsets.
Giving you a much more reliable estimate of how the model will likely perform on truly unseen data.
Exactly. And if you have imbalanced classes, you should use stratified k-fold, which ensures that each fold maintains the original proportion of classes.
And the out-of-bag error we keep mentioning. That fits in here too.
Yes. The out-of-bag OB error is that fantastic built-in validation estimate you get for free with random forests if you enable OOP-score true. It leverages those samples that were not used in training each specific tree. It acts like a sort of internal cross-validation. It's especially useful for large data sets where running full k-fold cross-validation might be computationally expensive because it provides an immediate, unbiased performance estimate without requiring any explicit data splitting.
Okay, so robust evaluation is key. That wraps up the pitfalls nicely.
Indeed. That brings us to takeaway number 4. To master random forests, we must avoid misinterpreting feature importance, understand the nuances of overfitting, and actively prevent it through hyperparameter tuning, ensure thorough data pre-processing, and select appropriate performance metrics validated by robust techniques like cross-validation or OOB error.
Now, what's truly fascinating, I think, is how we actually quantify the success of our random forest models in these real-world scenarios we've been talking about. After you've trained your model, the absolutely critical step is to assess how well it performs on data it has never seen before. This is where those specific evaluation metrics we just discussed become paramount.
Right. For classification tasks, we definitely look at overall accuracy, but we know that's not the whole picture. We need to dive deeper. We scrutinize precision, recall, and the F1 score to get that balanced understanding, especially, as you stressed, with imbalanced datasets where just looking at accuracy can be dangerously misleading.
And for regression tasks, predicting numbers.
Our focus shifts to metrics like mean squared error, MSE, which gives us the average squared difference between the predicted values and the actual values. Or often it's square root, the root mean squared error, RMSE, which is nice because it's in the same units as the target variable.
Lower MSE or RMSE is better, indicating smaller errors on average.
Exactly. And we also often look at R squared, which tells us what proportion of the variance in the target variable our model is successfully explaining. An R squared closer to 1 indicates a better fit.
And you keep highlighting the out-of-bag OOB error as something special for random forests.
It really is a unique and powerful feature. It provides that internal estimate of the model's generalization performance without you needing to set aside a separate validation set explicitly. Remember how it works. For each data point in the original training set, the OOB error is calculated by making a prediction for that point using only the trees in the forest that did not see that particular data point during their bootstrap training.
So it's like each data point gets evaluated by a subcommittee of trees that are unbiased towards it.
That's a great way to think about it. It makes the OOB error a genuinely independent and typically quite unbiased estimate of how the model will perform on new data. Often it correlates very closely with the results you'd get from a more computationally intensive k-fold cross-validation.
But OOB is much more efficient, especially for large data sets.
Exactly. You get it almost for free during the training process if you enable the option. It's incredibly efficient for quick performance checks or even for hyperparameter tuning in some cases.
But for the most robust, most trustworthy evaluation, especially when reporting final results or comparing models rigorously.
We still generally emphasize cross-validation as the gold standard. Techniques like k-fold cross-validation or stratified k-fold are essential. Systematically dividing your data into k-subsets, or folds, and then rotating which fold is used for training and which for validation. Repeating this k times, it just gives you higher confidence.
Right, it ensures that the model's performance is consistent across different random subsets of your data and isn't just a fluke outcome based on one particular train test split. It gives us much higher confidence in the model's ability to generalize to completely new, unseen data in the future.
Okay, let me try and illustrate the incredible power of doing this properly, particularly the hyperparameter tuning part, with a compelling real-world example. Let's think about predicting heart disease risk.
Okay, a critical application.
Definitely. Imagine we're working with a standard, publicly available heart disease data set. It typically includes various patient attributes, things like age, sex, type of chest pain, resting blood pressure, serum cholesterol levels, maximum heart rate achieved during exercise, and so on.
Right, typical clinical data.
Exactly. Now, we could compare the performance of 3 different models trained on this data. First, maybe just a single, unconstrained decision tree. Second, a standard random forest, maybe just using the default settings from a library like scikit-learn. And third, a carefully hyperparameter-tuned random forest, where we've used something like grid search or random search to find the optimal settings for parameters like nestimators, max depth, min sample sleeve, etc.
Okay, so comparing a basic tree, an out-of-the-box forest, and a tuned forest, what kind of difference do we typically see?
Well, when you look at the results from such a comparison, the difference is often quite striking. It really highlights the significant impact of both using an ensemble method like random forest over a single tree and the additional boost you get from hyperparameter tuning.
Give me some rough numbers, maybe.
Sure. For instance, in studies that have done exactly this on heart disease datasets, the single decision tree might achieve a testing accuracy of, let's say, around 0.77 or 77%. That's okay, maybe better than random guessing, but not great for medical decisions.
Right.
The standard random forest, even running with its default settings, typically provides a noticeable improvement straight away. It might push the accuracy up to, say, about 0.84 or 84%. A decent jump.
Okay, so the ensemble effect alone helps a lot.
It does. But here's where the hard work of tuning really pays off. The hyperparameter-tuned random forest in these studies often achieves a significantly higher testing accuracy. It might reach approximately 0.89 or even higher in some cases.
Wow, so going from 84% for the default forest to maybe 89% for the tuned one, that's another substantial leap, especially in a critical domain like healthcare.
It's a very meaningful improvement in reliability. And this enhancement isn't just confined to the overall accuracy metric. You typically see substantial improvements across all the key metrics we discussed earlier.
Like precision recall, F1 score.
Exactly. That tuned model might boast an F1 score of, say, 0.88 compared to maybe 0.76 for the single decision tree and 0.84 for the standard random forest.
Which indicates a much more balanced performance, right? Better at catching actual cases without raising too many false alarms.
Precisely. It signifies a much more reliable and balanced performance across the different types of potential errors, which is often what you really care about in practice.
And are these improvements usually statistically significant? Or could they just be luck?
That's a great question. Often, if you perform statistical hypothesis tests, like a paired t-test comparing the cross-validation scores, you'll find that the tuned random forest significantly outperforms the standard model across most, if not all, performance metrics. You might see very low p-values, for example, maybe 0.00012 for the difference in accuracy.
Which tells us with high confidence that the observed improvements are statistically significant and very unlikely to be just due to random chance. It's a demonstrably better model.
Correct. And beyond just the performance numbers, analyzing the feature importance in this specific heart disease prediction task can yield invaluable clinical insights. It reveals which patient attributes are truly driving the model's predictions. For example, attributes like maximum heart rate achieved during a stress test might emerge as highly significant, perhaps with an importance score of around 0.30.
Okay.
Age often plays a crucial role too, maybe with an importance of about 0.25. And perhaps serum cholesterol comes in at roughly 0.20. Obviously, the exact features and scores depend on the specific data set and model.
But these insights aren't just academic curiosities, are they?
Not at all. They can directly help medical professionals focus their attention on the most critical risk factors when diagnosing patients or assessing their prognosis. It can inform clinical practice, maybe suggest which tests are most valuable, and even guide preventive care strategies by highlighting key modifiable risk factors.
That's powerful. Now, this raises one more interesting question for me. How much does the specific tuning method itself matter? You mentioned grid search, random search, Bayesian optimization. Does one consistently give better results?
That's an interesting point, too. Studies that compare these tuning methods often show that different optimization techniques can indeed yield slightly different final results, although usually all tuned models significantly outperform the default. For instance, in that heart disease scenario, Bayesian optimization, being the more advanced technique, might sometimes provide a slightly higher final accuracy, perhaps reaching around 0.8905 testing accuracy,
Compared to...
compared to maybe grid search achieving 0.8878 or random search achieving 0.8842 for the same hyperparameter tuning task, given a similar computational budget.
So the differences between the tuning methods themselves might be relatively small numerically.
They often are quite small, yeah. But in critical applications like healthcare or finance, even a marginal improvement in accuracy or F1 score, even a less than a percent, can still have profound real-world impacts. It could mean correctly identifying more patients who need treatment or preventing more fraudulent transactions. So sometimes squeezing out that last bit of performance with a more sophisticated tuning method can be worthwhile.
That makes total sense. Every little bit helps when the stakes are high.
Exactly. This all really underscores our final takeaway.
Okay, let's hear it.
That brings us to takeaway number 5. Accurate evaluation of random forest models requires a suite of metrics beyond simple accuracy, and leveraging robust validation techniques like OOB error and cross-validation is essential. As shown in real-world case studies like heart disease prediction, hyperparameter tuning dramatically enhances model performance, leading to more reliable and accurate predictions.
Excellent. So let's do a quick recap now of all 5 key takeaways from our deep dive into the world of random forests today.
Sounds good. Takeaway number 1. We learned that random forests are fundamentally powerful ensemble models. They work by combining many diverse decision trees.
And they create that diversity using 2 key tricks: bootstrap sampling, or bagging, for the data each tree sees,
And random feature selection at each split point inside the trees. This combination is crucial for reducing overfitting and providing much more robust and accurate predictions than any single tree could possibly achieve on its own.
Okay, takeaway number 2, focus on the advantages. Random forests offer really unparalleled accuracy and robustness in many situations. They're incredibly versatile.
Yeah, capable of handling complex, high-dimensional data with various types of features, categorical, numerical, doesn't matter too much.
And crucially, they provide those valuable insights through feature importance scores. This combination makes them pretty much indispensable tools across incredibly diverse real-world applications, especially in fields like healthcare and finance.
Then, takeaway number 3 got into the weeds of hyperparameters. We saw that parameters like max depth, min sample sleeve, nestmators, and max features are absolutely critical for optimizing random forest models.
Right, they're the knobs that control the model's complexity and are key to preventing both overfitting on one side and underfitting on the other.
And finding the optimal values for these isn't guesswork. It requires using systematic tuning techniques such as grid search, the more efficient random search, or even advanced methods like Bayesian optimization.
Takeaway number 4 was all about avoiding common pitfalls to truly master random forests. This means being careful not to misinterpret those feature importance scores.
Understand the nuances of overfitting? Yes, they can overfit. And actively working to prevent it through that careful hyperparameter tuning and validation.
It also means ensuring thorough data pre-processing. Garbage in, garbage out still applies. And selecting the most appropriate performance metrics for your specific problem, not just relying on accuracy.
And always validating those metrics using robust techniques like cross-validation or the handy out-of-bag error.
And finally, our fifth takeaway really hammered home the importance of accurate model evaluation. We thought that it requires a whole suite of metrics, chosen carefully based on the problem.
And that leveraging those robust validation techniques like OOB, error, and cross-validation is absolutely essential for knowing how well your model will actually perform in the real world.
And our case study on heart disease prediction powerfully demonstrated just how dramatically hyperparameter tuning can enhance model performance, leading to far more reliable, more accurate, and ultimately more impactful predictions in critical applications.
Couldn't have summarized it better myself.
Okay, with all that we've discussed today, really digging into the nuances of random forests from their, core mechanics right through to the critical, almost artistic skill of hyperparameter tuning, I'm left with this thought, maybe a provocation for our listeners. How might we, in the future, perhaps combine the undeniable robustness and predictive power of ensemble methods like random forests with maybe even greater, more intuitive interpretability, perhaps borrowing ideas from simpler models?
Interesting.
Could we create AI systems that are not only powerful and accurate, but also fundamentally more transparent and trustworthy, especially when we deploy them in really critical, high-stakes applications like medicine or justice? Something to think about.
Definitely food for thought. Balancing power and transparency is a key challenge going forward.
That's all for now, folks. Please like, share, and subscribe for more like this.